Okay, greetings everyone from North Carolina. Alyssa was doing so well there. She's like Stephen Colbert, watch out. I want to thank you to Alyssa and all the team at ABMR for setting this up. And I'm really, really sorry that I can't be there to have a good time with you all. What I want to do today is use my 40 minutes, which I hope I still have, to tell you a story about our work developing a measure of humans' pace of biological aging for use in prevention research. So you may know that I am not a gerontologist, not at all. Most of my career has involved the study of mental disorders, and mostly in children and adolescents and young adults. So this story is about a major disciplinary change for me. The work started here. This slide shows the well-known accumulation of multimorbid diseases across the lifespan. Advanced age is the strongest risk factor for all non-communicable diseases. So if the aim of prevention is to prevent the onset of these diseases, then the red arrow you see here shows the ideal intervention point has got to be by the 2nd to the 5th decades of life. Now, I'm going to be telling you about quite a journey, so I thought an outline might help. And let's just begin by figuring out how the research works. So our team has been tracking the health and development of a birth cohort of 1,000 individuals born in 1972, the Dunedin study. The study is well known in the pediatric literature, where it's generated more than 1,000 published findings on child health and development over the years. The study members have now reached their late 40s. So we believed that we were pretty well situated to contribute knowledge about the 2nd to the 5th decades of life. Looking back now, it's become clear that I was overly smug about this, but that's part of the story. So first, I want to introduce you to the study because that's our main research tool. So here you see the study design. At the top, 1,037 babies were enrolled at birth. They were all the babies born in one city in one calendar year. There were no exclusionary criteria. We took every child. And ethnically, the cohort is of white European descent. If you look down the left column, you see this shows us the ages of data collection. There have been 13 assessments since babyhood. Each time we assess the cohort members, each of them spends a full day in our clinical setting for data collection. So now we've added another half day for neuroimaging. Down at the bottom, you see that the last completed assessment wave was at age 45 in 2019, when 94% of the cohort took part. So it still represents the full variation in the population with no attrition bias or healthy survivor bias. Now, when we first proposed to study aging in young adults in their 30s and 40s, the peer reviewers at NIH scoffed at our proposal. And actually, they hated our grant application on the grounds that there would not be any variation on measurements relevant to the study of aging in people that young. So this slide shows you composite faces from digital photos of 10 female and 10 male Dunedin cohort members. The photos were taken within 60 days of their 45th birthday, and I have to say, they do look pretty young. However, these composites are 45-year-olds too. They comprise the 10 fastest aging members of the birth cohort. So the first thing we observed was that there is definitely variation in aging among people many years before they're considered to be older adults. Now, all the people in this birth cohort were born the same year, and in fact, in the same maternity hospital. There's obviously enormous variation in our participants' aging, as it can be seen in their faces. So we set out to quantify this so that we could study it. Now, to explain the background to what we were trying to do with our research, I'm going to contrast three very simple conceptual models. On top is the model I learned in gerontology courses I took at USC back in graduate school. I learned that disease onsets in late life, it leads to frailty and thence to death. and we were told study disease and frailty. The middle bar shows you a subsequent newer model, which gained traction soon after. It pointed to the importance of earliest life for aging. For example, the theory of developmental origins of health and disease pointed to perinatal factors that predicted late life disease and mortality. Plus, there were findings about childhood deprivation and adversity predicting disease. But these empirical findings about early life still left a black box in the life course. Now, it's truly remarkable that risk factors present at birth or in childhood can statistically predict late life disease, frailty, and mortality. But what we don't know is how this happens. What is going on in the second, third, fourth, and fifth decades of life? The predominant assumption was that early risk must accelerate the aging process, and that's shown on the bottom yellow bar. But when we came to this, there was no empirical work testing this assumption of accelerated aging in the younger decades of life, and we decided we could fill this gap. So when our cohort was first entering their 30s, we knew we wanted to convert this study of early child development into a study of aging. And so we began at that time to collect measures used every day in geriatric medical practice. And I'm going to show you a few photos of some of the assessments. We repeat these data collection protocols every time we assess the Dunedin study members as adults. These are just examples to give you an idea. We're keen on data sharing, and you might see some measures that you could use, and so do get in touch. I'm going to go swiftly because these measures are already familiar to most of you. So here you see postural hypotension, then bone mineral density in a full body DEXA scan. We have a physical function protocol, and here you see 30-second chair stands. We have an auditory test assessment protocol, and here you see detecting speech in background noise. There's a vision assessment protocol. Here you see the optic nerve scan. There's everybody's favorite of the day is the dental exam. And we also have a respiratory and lung health assessment protocol with, here you see plethysmographic testing of lung capacity. And we do quite a few interspersing with clinical interviews. What's shown here is the life history calendar, but there are also psychiatric and substance abuse interviews and assessments. And we interview the study members about financial and health knowledge and other topics. We draw heaps of blood for genomics and biomarkers. When we get to this point, I'm supposed to say one aspect of the Dunedin study that makes it exceptionally valuable for the study of age-related change is that the study was designed to be multidisciplinary from the outset, before I ever joined it. We have measured many of the constructs of interest to aging science repeatedly since the preschool ages. So the study now has the longest running series of repeated clinical measures in areas such as hearing, vision, dental health, motor skills, and lung function, in addition to cognitive testing, which I'm going to show you in a minute. So having such unique baseline data helps us to say with great confidence whether midlife measures show decline from a younger, healthier level. So another thing we do with the Dunedin cohort is administrative data linkage. We link into, these are Scandinavian style national registers. We have medical records, social welfare, pharmaceutical prescription records, insurance claims for accidental injuries, and these are going back over the lifetime. Study members also consent for us to download their credit ratings. At age 45, we began brain scanning, and we did this in collaboration with Ahmad Hariri. I'm showing you white matter hyperintensities here, and I'm showing you these because according to the neurology literature, white matter hyperintensities only begin to be detectable about age 60. The histogram on the right shows you we did find variation at age 45, and I think we see this because we have very sensitive scan resolution. Now, it's sad that we don't have brain imaging data from early life. But as you know, during the 80s and the 90s, when the Dunedin study members were young, scanning was simply not done on healthy children living out in the community. And in any case, in those years, scanning was way too expensive to scan 1,000 people. What we do have is measures of the function of the brain collected at age 3 in 1975. And here you see how each of the 1,037 children were individually tested at age 3. Now, from the data collected at that time, we created a composite summary model to measure each child's brain function. Each child was examined by a pediatric neurologist. They took the Bailey Motor Skills Test, the Raynell Test of Receptive Language, the Peabody Picture Vocabulary Test, and after the testing session, staff examiners rated each child's behavioral self-control and self-regulation. So an obvious place for us to start then was testing how key measures from gerontology research might be related to these measures of early life brain function. Now I'm going to show you some midlife outcomes of toddler brain function. So cognitive processing speed is known to be a sensitive measure of age-related cognitive decline. We've tested processing speed at every age right up to age 45. On this slide across the bottom, you see age 3 brain function. On the left are the children with the least healthy brain function as 3-year-olds, and on the right are the children with the healthiest brains. The 3-year-olds who had the poorest brain health have processing speed almost a standard deviation slower at age 45 than their cohort peers who had the best brain health as a toddler. We measured also the caliber of venules. These are microvessels in the retina of the eye. It's a non-invasive indicator of small vessel disease in the retina, but also in the brain, at least in the occipital lobe. It's a widely used biomarker in research on risk for stroke and dementia in older adults. The 3-year-olds who have the poorest brain health have venular caliber almost half a standard deviation wider at age 45 than their cohort peers who had the best brain health at age 3. Now I'll look at walking speed. Gait speed is a highly sensitive marker for age-related decline and for early mortality in the elderly. It's a key measure in the study of functional aging. The 3-year-olds who had the poorest brain function have gait speed almost a standard deviation slower at age 45 than their cohort peers who had the best brain function as toddlers. So what does this mean? When you begin a study of older adults and some of your participants show signs such as slow processing speed or wide retinal venules or slow gait speed or even memory problems, it's not at all safe to assume that this reflects a decline of recent origin. In fact, individual differences on many key gerontology measures have their etiological roots very early in life. So now let's move along to talk about measuring the pace of aging. We thought of aging as a life course process. First, we know that exposures that cause age-related diseases do accumulate starting from early life. We know that changes to physiology occur many years before disease diagnosis. And we know that organ damage is difficult to reverse fully once it's established. And all this together suggests that preventive interventions should begin early if we aim to slow aging and extend health span. We think we need to understand aging processes in young people if we intend to intervene and change these processes. But how can we measure how fast a young person has been aging? The first thing we hit was a major barrier. Now, to our surprise, there was actually no accepted measure of aging when we started all of this. This shows you a 2020 paper reporting a lack of consensus. The authors are a list of many of the heavy hitters in gerontology. So early on, it became clear to us that we were going to have to figure out how to measure aging. And in fact, we began working on that with Daniel Belsky when he was a postdoc at Duke. Now, I suggested then that we ought to pay attention to what a group called geroscientists were saying about their operational definition of aging. They defined aging as the gradual, progressive, coordinated deterioration of physiological integrity across multiple bodily systems. In other words, decline across organ systems that is synchronized and happening simultaneously. Now, in the Dunedin study, we had been tracking 19 biomarkers since the 1990s, when the 1,001 study members were in their 20s, which you see here. Now, our first gut check was, would this cohort show evidence of mean level decline on the biomarkers across the middle decades of life? Remember, the NIH peer reviewers were skeptical about that. So I'll show you 4 examples. I'll show you 4 examples. This one you see is mean VO2 max. It's a measure of cardio fitness on an exercise bike, and it declined steadily from age 26 to 32 to 38. And I'm sorry, I haven't updated this slide yet to include age 45 data, but trust me, the cohort's mean fitness keeps on getting worse. The cohort's mean lung function also declined from age 26 to 32 to 38. The exception to this is cannabis smokers, whose lung capacity is not getting much worse, and you can guess why. The mean blood pressure rose steadily from age 26 to 38. And we saw the same pattern in prediabetes testing. Now, I'm not going to show all 19 biomarkers one by one, that would be boring, but this slide depicts an eyeball look at the data for the 19 biomarkers. Virtually all of them did show gradual, progressive, coordinated worsening of physiological integrity, and this was across multiple bodily systems. But some of our cohort members were aging fast or declining fast on these, and others were hardly declining at all. So the next step was to capture these differences between individuals. So to do this, we calculated 19 growth curves, one for each of these repeated biomarker measures, and then we combined the curves to model what we called the pace of aging. Each individual in the cohort gets a score, and that represents the gradual change that is consistent across all of the 19 biomarkers. So it captures that concept of synchronized change. Now, the green histogram shows you the resulting distribution of the pace of aging scores in the cohort. It's plotted in years of physiological change per chronological year. On the left are some individuals who show almost no biological aging between age 26 and 45. They've been remaining young. And on the right, some cohort members aged almost 2 years per chronological year over that period. Now, we validated the pace of aging score by testing if it predicted cohort members' outcomes on all our measures of cognitive, perceptual, and sensory motor capacities. The full report was in Nature Aging this summer if you'd like to see these data. I'll just give you a few concrete examples. So here you see that the fast agers had poorer balance already at age 45. The white circle reminds me to tell you that each data point on the slide represents 20 of the 938 cohort members who took part at age 45. The slow agers are on the left, and they have higher, better balance scores. The fast agers also had more decline on tested cognitive function from childhood to age 45. And the fast agers even had faces that were rated as older looking at age 45. Now, we looked inside the brain too. A faster pace of aging score was associated with a thinner cortex and a smaller surface area of the brain, assessed by MRI at age 45. The blue shows the brain parcels that passed correction for multiple testing. Now, it's already well known what some of the best early life predictors of early mortality are, and you see them here. and Alyssa talked to you about them as well. There's familial longevity, there's low social class origins, adverse childhood experiences, often called ACEs, poor child health as a child, low intelligence as a child, and low self-control as a child. This slide shows you that all of them predict faster pace of aging at age 45 as well. So, chronological age or biological age? We found a lot of variation in biological aging already as young as age 45. What does this mean? First, entitlement to Social Security and other supports for post-work life, like Medicare, are based on chronological age. Second, health disparities mean that for high social class groups like us, 75 is the new 65. We well-educated, white-collar desk workers get support years before we actually need it. But for low social class, low education groups, 55 is biologically the new 65. Many blue-collar workers cannot sustain physically demanding occupations until they're entitled to support. Keep in mind, when the Social Security system was established in the United States, the mean age at death was 65. The government thought then that they'd never have to pay out for people whose bodies wore out. There have been several reports this year in The Lancet, JAMA, and the New England Journal of Medicine documenting rising levels of frailty in Americans who are still of working age. This has implications about how policymakers define entitlement to supports for post-retirement life and health. We're interested in this notion of accelerated aging as a social justice issue. It's kind of a new way of thinking for us, but it came to mind this year because of what our data were telling us. Now, to shed a little more light on it, we had interviewed the Dunedin study members about their financial knowledge. What did they know that would help them be ready for retirement and old age? We did not want our measure to be a measure of their just arithmetic skills or just a measure of their verbal intelligence. So we did something new. Interviewers had a discussion with each study member, open-ended, about finances, and asked them a series of questions like the ones you see here. These are questions that were meant to ask about study members about their understanding of principles like compound interest or inflation, or spreading risk across a financial portfolio, and so forth. The transcript of each study member's discussion was brought to Duke and coded later. This shows you that the quality of their financial knowledge for 5 levels of the pace of aging co-varies. The slowest agers on the left have knowledge levels almost a standard deviation better than the fastest agers who are on the right. Financial principles can be taught. We've run this analysis controlling for IQ, and that's not the explanatory variable. So now that we know that the people who are aging the fastest and who need to retire the youngest need more financial planning now to do so and to be ready, we could teach them this in a better way. So in summary of this section, the pace of biological aging can be measured in young people, and it validly predicts physical limitations, cognitive decline, sensory decline, and even facial aging and brain aging. But we needed an exportable version of the pace of aging that other people can use. It's not very useful having a really cool measure built from 20 years of repeated biomarker measures if nobody else has that kind of data. And it's very hard to find. In fact, no other study we know of does have it. So what this meant was that nobody could try to replicate our work, nobody could build on it, so I would never get cited again, and I think that would be very sad indeed, at least to me. So our team got really motivated to develop an exportable measure. So we'll talk now about converting the pace of aging to a blood test. Now, a particularly urgent need for an exportable measure of the pace of aging is for testing the efficacy of anti-aging therapeutics. Alyssa brought this up earlier about her excitement about these therapeutics. In case you haven't noticed, we baby boomers who do not want to get old and who do not want to die are a huge and motivated market, and we got lots of money. And products marketed as reversing aging are popping up all over the place now. Here's one example. It's a daily capsule that promises to keep your telomeres from eroding. And just to add more light relief, last month in Iceland, I found this supplement that purportedly reverses aging. It's made from lobster shells, something they have a lot of in Iceland. Obviously, randomized clinical trials are needed. So just seriously, this is a serious and growing biotechnology business. There are federally funded clinical trials. There are compounds in the pipeline, and there are lots of biotech companies working on therapies to slow aging. There are also many trials of behavior change interventions, such as physical activity and dietary management. All this is referred to as the geroscience agenda. The idea is that advanced aging is a cause of all diseases, so if you can slow aging, you can prevent them all with one silver bullet. These silver bullets are already available for yeast, for worms, and mice, and research is pretty far along for treatments to slow human aging. But the trick is, to give these therapies their very best chance, you have to start the treatments as prevention before late life organ damage is too far along. Now, all these RCTs of prevention before late life are not going to be able to use disease or death as their outcome. Those outcomes are too far in the trial participants' futures. They're going to need measures of, like, the pace of aging. They need measures for pre-treatment baseline. We need to know who will respond best to anti-aging treatments, fast agers or slow agers. Nobody knows that yet. And we need pace of aging measures for tracking post-treatment outcome and long-term follow-up. Are these treatment effects going to last, or are they going to fade out? Nobody knows yet. We need cheap, easy, repeatable measures of the pace of biological aging to use as randomized clinical trial outcomes. And a good measure has got to show that it's sensitive to change in trials of anti-aging therapies. So our next step was to translate our longitudinal pace of aging measure into something that could be done as a blood test. We did this translation by deriving a DNA methylation signature of the pace of aging. We were following the work of Steve Horvath and of Hannum and others who had already been using the methylation approach to measure age and aging. We looked for a DNA methylation signature. It's called Dunedin PACE, for pace of aging computed in the epigenome. We published this in eLife in 2020, and there's a new update this month in medRxiv, now under review. And here you see the link on the slide. Daniel Belsky is there at the meeting with you, and he can describe more about it. So this work required us to learn to work with whole genome DNA methylation data. This is something our team has been doing for about the past 7 years. We use the pace of aging measure that I've already told you about as the training target. So the training is based on a longitudinal change measure. The elastic net regression process was used to identify probe sites in whole genomic methylation data that map onto variation in the pace of aging. So as a result, researchers can now measure the pace of longitudinal aging in their own research participants, even if they don't have a longitudinal study or lots of biomarkers. So hang on, I just skipped sorry, a slide skipped. Oh well, we're now publishing validity checks. I can swiftly show you the key ones people usually look for in a good measure of aging. Here in Daniel's work, Dunedin PACE predicts mortality in the Framingham Heart Study. The red shows earlier death for faster agers. faster Dunedin pace predicts early mortality in the American Health and Retirement Study 2, and the right side of the slide shows it also captures the well-known disparity between Black and white Americans on age at mortality. It may interest some of you to know that our measure in the HRS is obtainable from the HRS along with age clocks. HRS also has lots of health data for those who are keen. In the Texas Twin study, Dunedin pace is accelerated in adolescents who experienced early life adversity. Family disadvantage is shown on the left in pink, and neighborhood disadvantage is shown on the right in yellow. And in our own UK e-risk study, the Dunedin pace is faster among young adults who grew up in poverty in Britain. Now, this slide compares methylation aging measures in ADNI, the Alzheimer's Disease Neuroimaging Initiative. Dunedin pace is shown on the right. It has the best capacity to differentiate among groups who had patients who had no cognitive impairment, shown in blue, mild cognitive impairment, shown in yellow, and diagnosed dementia, shown in gray. The dementia patients are aging the fastest. This is potentially important because NIH intends to fund midlife prevention trials for Alzheimer's disease, but for these trials, they'll need an outcome measure that can be used in people under 60. It takes too long to wait until midlife trial participants reach their late 70s and early 80s to see if they get dementia. So you've undoubtedly heard about the age clocks, and you're wondering by now how Dunedin pace is different. I'm going to leave that comparison between Dunedin pace and the clocks for Daniel to tell you about later in this conference. So I'll just talk about our research agenda going forward. We're now exporting Dunedin pace to 19 cohort studies to test how it's going to fare and what its limitations are going to be. So we really want to push the edges of it. There'll be key tests in the sexes, different age groups, wider geographies and nationalities, and different ethnic groups. Because if geroscience is going to improve aging in the whole population and reduce the burden of age-related disease on societies, then the interventions are going to have to reach out to include the people who are aging fastest, who are suffering the most costly diseases, and who are dying youngest. Up until now, intervention trials have mainly included educated white volunteers. This slide shows you the 19 cohort data sets that we've lined up for this stage of the validation work. Our hypotheses are on the left, and the data sets are on the right. The bright blue signifies that the data set is African American or Latinx in ethnicity. And this is an invitation from me. If you have a sample that you would like to join this effort, please do let me know, because we need more data sets to really test the edges of the limits of this measure. Our other next step is to determine whether we can model specific kinds of aging. We're going to follow up the cohort at age 52 soon, and using those Dunedin study data that I showed you at the very beginning of this talk, this is going to give us the waves of repeated measures that we need to model the growth curve slopes of decline over ages 38, 45, and 52 for inflammatory aging, microvascular aging, functional aging, cognitive aging, sexual aging, social aging, and facial aging. Now, the code to compute Dunedin pace is available on GitHub if you're interested in computing it yourself. The 2020 version is posted now. The 2021 version is coming soon. You can also have it done commercially for you by a nice company called True Diagnostic. Sorry, the slides are kind of not changing properly. There you go. A nice company called True Diagnostic who's happy to do it for you. So what are the opportunities that are going forward for this kind of work? We need a lot more basic science knowledge about biological aging in still healthy young to midlife people. We don't know that aging works the same in midlife and in late life. We simply don't know that. We also need to find some new intervention targets, research to identify new early life targets or midlife targets that can slow the pace of biological aging would be great. And we need to focus a lot more on health disparities. You know, it's not escaped my notice that the people who are most enthusiastic about the neuroscience agenda to slow aging tend to be wealthy angel investors and biotech entrepreneurs. But who needs anti-aging therapeutics the most? Poor people. So thanks to our research teams at Duke and in New Zealand, and thank you very much to this really great audience that I can't see for the opportunity to let me tell you about this new work.
Thank you so much. Thank you, Terrie. Absolutely amazing and mind-blowing body of work and exciting next steps for all of us. So I'd like to invite you up. We have a little bit of time for Q&A, so you can step up to the microphone and Terrie will hopefully, there you are.
Alyssa,
so we have a lot of questions and comments from the chat. So our first question, I think from Tika in person, and then we'll take one from the chat if Elisa wants to represent our virtual attendees.
Sounds good, but Alyssa, your talk was so stimulating too. A lot of people will have questions for you, so don't run away.
I'm here all weekend. Thank you.
Do your best, Steve Colbert.
Hi, Terrie. Tika Hall, University of Pittsburgh. So I've got a comment, something I want to tell you about, and then a piece of advice for all of our early stage investigators, from graduate students to postdocs and assistant professors here tonight. First, a comment is I'm in Pittsburgh, and I want to tell you that Karen Matthews, who is an incredible scientist, your study is her favorite study ever, and she loves talking about it. So if you didn't know that, now you know.
I didn't know that, but that's great.
So here's the piece of advice.
I feel the same way about Swan.
So when Alyssa was introducing you, she said that for this kind of aging work, that you sort of have a litmus, I'll use the word, she didn't, to do longitudinal research. And to do longitudinal research, you have to sort of create a cohort. And so advice for young folks on how you do that, because it is not an easy thing to do and expensive and obviously longer than a 5-year grant.
It's hard to get started in that. It was hard when I got started. You know, my advice could be do what I did and join an existing ongoing cohort study. I was able to do that in the 1980s because there were existing ongoing cohort studies. These days, there are a lot fewer of them, and I wish we had more. Britain still has some, Scandinavia still has some, the United States has struggled to start some, and we'll see. We really, you know, wish them the best and hope they work out. ABCD seems to be doing quite well. So getting in touch with those studies, joining them with your ideas for data you want to collect, and really, you know, that's the best way to get involved in that. The other way is to really learn about the ongoing studies, because they're all underpublished. So people collect lots and lots and lots of data, and we just pray and hope that young people will come along to us with good ideas so that we can share and get the data used. So I don't think you would ever be turned away, and you should just be brave and approach people, and approach the PIs who have existing longitudinal studies.
All right. Terrie, thanks so much for being here. This is Elisa. So I have a question from Howard Friedman, who asks about some of the most interesting questions involve individuals who start low, kind of worse, I imagine, faster biological aging, but end up high, healthier, and vice versa. What are their pathways? So I guess for individuals, did you look at individuals who were perhaps aging slowly and then, switched categories or vice versa? What potential pathways those would be?
So we have some different backgrounds and aspects that able to have has improved. Our goal for the similar to the studies of their field and to kind of I think more to run work, especially in people. I mean, so look, noting so elders actually recall less of.
Yeah, Rob, you just your 9 members also increase your time clear and have them give more motivation. 2 days medication.